Now, going back to thinking overall about rigid body kinetics. The equations of motion are Newton's second law. So that says add up all the forces on the chosen body, and that's equal to the mass of the chosen body times the acceleration of its center of mass. Okay. Now we know what this is, we know what this is, we know what this is. So we're good on Newton's second law. And then the second one, equation of motion, second vector equation of motion, is the moment equation, rotational Newton's second law. And that says that if you add up all the moments around the about point, that's equal to the mass moment of inertia around the about point times the angular acceleration vector. And then there are some restrictions on what that A is. A is either, what are the possibilities? Yep. And does everybody have a fixed point? No. Only bodies that have a hinge that connect it to the ground or whatever your coordinate system is. And for things that don't have a fixed point, what's the other option? Center of mass, that's right. Okay, so we're okay with this. We're okay with the idea of a fixed point. We know what the angular acceleration is. So we just have two more definitions we need before we can do problems. We need to talk about the definition of the mass moment of inertia. And we need to talk about what a moment is. Okay? So we're going to start with the mass moment of inertia. About a point. This is the way to think about it. You'll see that usually people, when they're talking about this, just call it the moment of inertia. The variable that we're going to use for this is going to be a capital I sub A. So we'll get to that as we go through because you'll see from the definition what the units are. Okay, so there's one thing to be really careful about here. So people are going to just call it the moment of inertia, but that obscures an important difference with something that's going to come up in the next few weeks in D-form. So be careful. In D-form, there's the area moment of inertia about a point. Just like this one, people call it, so it's called just the moment of inertia. And it's given the variable name capital I sub A. Okay, So it's really easy to get these two mixed up. The area moment of inertia is a measure of, so it measures a cross section's resistance to bending the mass moment of inertia measures a rigid body's resistance to rotation. So this is the one that we're dealing with, talking about the ability to rotate a rigid body. And you can think of the mass moment of inertia as being exactly a rotationally analogous to mass in translation. Okay, like a mass is something that resists acceleration. The mass moment of inertia tells you how well a body will resist angular acceleration. Okay, so if you have a big mass moment of inertia, it takes a lot to get it rotating. If you have a small mass moment of inertia, it's easy to get it rotating. And that's without any consideration of what other loads are acting on it, whether it's on the ground, whether there's friction or anything like that. Out in outer space, if you ran into a semi truck, it would hurt. You know what I mean? Because it would be really hard to accelerate it down to rest. You know what I mean? And that doesn't have to do with its wheels being on the ground or whatever. That's just a property of its mass. And it's the same thing if in outer space, if you tried to get if you had a semi truck in outer space connected to a hinge, that would be so weird. But once you got like used to that idea and you tried to rotate it, it would be hard. And it doesn't have anything to do with friction or anything like that. It just has to do with the mass moment of inertia. Okay. So the integral definition of the mass moment of inertia. No, let me not give you that yet. Let me tell you what the idea is. So something with a big mass moment of inertia has a lot of mass situated far from the axis of rotation. Okay, so let me show you an example. In gymnastics or diving, any kind of acrobatic sport, there are different ways you can position your body to do flips, you know. And so I'm going to think of sort of the two extreme versions of this. Okay, so here's one way, you know, if someone does like a double backflip like this, they get a lot of points for that because it's really hard. Or someone could do a double backflip this way. Well, it's also very hard, but they get a lot less points for it because it's not nearly as hard as this. Okay. You get a lot more points for this because it's hard to get this rotating. And since it's hard to get this rotating, you have to get up a lot higher in the air in order to finish 2 flips with your body in this position. Someone who's really good at that tuck tight position, they don't have to get up that high in the air to finish 2 flips like this. So relatively to the other one, this is easy to rotate. And the reason is, so either of these have fixed points? No. So you have to think about this then as the axis of rotation being their centers of mass, which is like here and here. What? Well, that's pretty close to where it is, but the center of mass is, yeah, it's somewhere in your torso. But just the way these equations work mean that in order to think about this intuitively, you have to choose the center of mass as what it's rotating around, unless it has a specific hinge to the ground. It does, yeah. So let's think about what's going on a little bit. So say this is the same person, like their first time before they get tired, they do their double flip like this, and at the end they do it like that because they're tired. So this person has the same amount of mass, okay? So it's not harder to rotate this because the mass is higher. The difference is that here you can see if you broke this person up into little infinitesimal pieces of mass, a whole bunch of that mass is positioned at a big distance from the axis. Okay? And over here, the whole idea of this position is you're trying to get every part of your body as close to that axis of rotation as possible. Okay? So this has a big mass moment of inertia, and this has a small mass moment of inertia. Okay, so in this case, mass is situated far from the axis. And so that is a big mass moment of inertia. And in this case, mass is situated close to the axis. And so that's a small mass moment of inertia. You see the same thing in figure skating when people do the, so when people do their spins at the end of the, oh, you know why they do that spin at the end of the routine? Because they're super dizzy after they do it. So it'd actually be a lot more entertaining if they did it at the beginning. But okay, so someone starts their spin and they're all stretched out and they're going slow, and then the music swells and they pull their arms in and spin really fast. It's that same idea. The axis is down through their body. And so when their hands are out and their legs out like this and their head's back, they have more mass situated far from that axis of rotation, and it's hard to rotate that. And then when they pull everything in as tight as they can to that axis, they spin really fast. Now, mass moment of inertia also has an integral definition. And just like with centroid, I'm going to give it to you. I'll do like one derivation, but mostly you're just going to use formulas for simple shapes. So the integral definition for the mass moment of inertia about a point. We're only doing this in 2D, so when I say a point, that would be an axis in 3D. And that definition is I sub a is equal to the integral over the whole area of r squared dm, where dm is an infinitesimal amount of mass and r is the distance from the point A. That's also, if it's in 3D, we're talking about an axis, but in 2D, that's a point to that piece of mass dm. Okay. This tells us what the units are. Yeah, so the SI units, well, what does that integral tell us? What are the units of dm? Kilograms. What are the units of r squared? Meters squared, so the SI units are meters squared kilograms. I guess people actually do it kilograms, meters squared usually. So I'm going to do the mass moment of inertia of a disk about its center. But I want you to notice a couple things about a disk, because this is going to be an important thing to keep straight. So a disk, okay, so let me draw this sort of from the side, okay? Even though we're doing two-dimensional problems, you can have rotations about multiple axes in two-dimensional problems. So like, for example, the one that I'm going to do first is a rotation of this disk about this axis. Okay, let's call that the z-axis. But you could also do a two-dimensional problem where all your calculations are in 2D, but you need to know the moment of inertia of a disk about this axis. And just the same way you could do it. So if this is the x-axis, then this would be the y-axis. So all of these have this same about point A at the center, but it's different calculations to figure out what the mass moment of inertia is about these axes. Okay. Notice that because of the symmetry of this disk, the moments of inertia about two of those axes are the exact same thing. Can you see which those are? So the moment of inertia about A rotating around the x-axis is the same as the y. Yep. But the mass moment about z is different. These are the ones that are like paddles. This is the one that's, I mean, it's like a wheel. I'm going to call it a blade because we're going to have to use this idea for other shapes too, rectangles or whatever. You have to think about whether it's trying to slice you or slap you as it rotates. You know what I mean? Okay, so let's do. Oh, I already wrote that, didn't I? Okay, so let's do the mass moment of inertia. Where A is the about point, about that axis Z, and we're going to use this definition. So over the whole mass of R squared dm, okay? And since it's a uniform thickness all the way through, we can just think about sort of the mass density per area. So we'll divide the total mass by the total area, and then any area we multiply by the mass, that'll tell us how big the mass is of that piece. Okay, so the total area is just pi r squared, and let's call this a capital R to differentiate between that and the R in this formula. So the radius of this is capital R. And the mass of this thing we're going to say is m. Well, let's make that a big M too to differentiate. So the total area is pi r squared, pi big R squared. And so the mass per area I guess big M over A is just big M over pi r squared. Okay, so now notice that what I've done here is I've given us a way to, instead of doing this all in terms of mass, which can be a little tricky to think about mathematically, now we have a way to represent this any increment of mass in terms of an infinitesimal increment of area, because we can just come up with our expression dA and then multiply it by this, and that gives us our dm. Okay, so who's with me on that? Nobody? Good. Okay, so dm now is equal to we want m over a dA, and so that is m over pi r squared dA. Okay. So now we can do this. The variable that we're integrating over isn't mass, it's area. And now we have to think about how we're going to break up this area into infinitesimal pieces. That's always like when you're using any integral formula, any integral definition, that's kind of like the heart of the problem, you know, figuring out how to break it up into infinitesimal pieces. So here's how I'm going to do it. So here's our disk. And here's our about point. And we're going to break it up into infinitesimal. Okay, so what do we know about this ring? We'll say that the distance here is little r, okay? And we'll say that the thickness is infinitesimal, and it has a value dr. Okay, so since this thickness is infinitesimal and this radius going to it is finite, we don't have to worry about, when we're talking about the distance from the center to here, we're assuming that that represents every point on this ring. You know, to get to the outside ring would be like, you could imagine it would be like r plus dr over 2, but dr is 0. This is finite, you know. To get to the inside ring, it would be r minus dr over 2. But again, that's just r. Okay. So how can we come up with an expression for the area of that infinitesimal ring? So this is our, this is our infinitesimal area. Yes, so that's what we're going to do. So what we're going to do is break this apart somewhere, stretch it out, and now it's just a long, infinitesimally thin rectangle. Okay. And so to calculate that area, it's going to be the circumference of that circle times the thickness. Okay. So dA is equal to 2 pi r dr. It looks like this once you stretch it out. You have a length of 2 pi r and a thickness dr. Okay, and we're just taking the area of that rectangle. That is a trick that comes up in integral definitions of all sorts of things when you're doing circular shapes. And now that we have that, so we have dA, and the benefit of what we just did is now we have it expressed in terms of r, and look at the definition. There's an r in that definition that represents the distance from the center of the disk, or from the about point to the point that you're looking at. Notice that for everything that we have here, this is a whole bunch of points, right? But every one of those points is a distance r from our about point. Okay. So now we can represent this integral. So our I sub a is equal to the integral of r squared times dA, which is 2 pi r dr. We're missing one thing. We didn't want r squared dA, we wanted r squared dm. So we have to multiply all this by this conversion factor. So since that's a constant, we can pull that outside. So pi big R squared. Okay. The last thing we need is the bounds of integration. What R values are we going to integrate this over? 0 to big R, yep. You get a cancellation here. And so I sub a is equal to m over r squared and let's pull the 2 out here too, that's a constant, times the integral of little r cubed dr. And so that's 2 big M over big R squared times little r to the 4th over 4, evaluated from 0 to big R. And so I sub A is equal to 2M over R squared, big R squared, times, plug in the big R value for little r, you get big R to the 4th over 4. Plug in the 0, you get 0. And so this comes out to be 2 big M, big R to the 4th over 4 big R squared. And our final formula then is 1/2 big M R squared. And so now we have this formula, you know, and that means that we never have to use this integral definition again for a disk rotated about its center. They come from the integral definition. For 4 simple shapes. You don't have to use the integral definition very often, maybe never, because if you come up with a shape that you don't know the formula for, you just ask your smarter friend to derive a formula, and then you use the formula. Okay, so the first one is a slender rod. This is the only one I got to before. So we're assuming that the thickness, the width, is negligible. The coordinate system we're going to use for all these is centered at the center of mass. Origins at the center of mass. And we'll call this X, Y, and Z. So with the about point at the origin, first about the x-axis, if you're assuming that that thickness is 0, then that's not a very good assumption if you're doing things rotating about the x-axis, but it would be 0 there. What you'd really want to use in that case, so if you have like a shape like this, a long cylinder, and you're dealing with rotations about the x-axis, you'd want to treat that as a disk. You'd get nonsense results by assuming that the thickness was 0. You'd use its actual radius and say it's a disk. But about the y-axis is the same as about the z-axis, and in both cases it's 1/12 times the mass times the length squared, and the length is this. Those should be parallel to the z-axis. So this is L. Okay, the next one is a rectangular plate. And we're going to make the assumption that that it has a negligible thickness. So I'm going to call this a thin rectangular plate. Um, and the dimensions, I'll call this B. And this C. And then the coordinate system, I'm going to call that X, that Y, and that Z. So for rotations about the x-axis, these distinctions we're going to use pretty often. So you're going to have to, little by little get used to thinking about how this thing is moving, what we're talking about when we talk about a rotation about x, a rotation about y, z. A rotation about x, this thing is thin, so you're imagining this is like throwing flicking a card or like throwing a Chinese throwing star, you know, like a blade. Okay. The other two are, so this is like a blade. The other two are like paddles, like a paddle wheel. Okay. Um, so about the x-axis, mass moment of inertia is 1/12 times the mass times the quantity b squared plus c squared. Notice that as let's say that you make that b get smaller and smaller, as it starts to get close to a negligible thickness, this thing gets close to like a rectangular stick, and that formula turns into that formula. Okay, so those agree with each other in that sense. Okay, now rotations about y. Now think of looking at the xz plane from the positive y-axis. What does this shape look like? It looks like a rectangular stick, right? We can't see the thickness into the page. And so we would expect this, so, about the y-axis, we expect this to look like the formula for the slender rod. And so that's what we get. And what's the length that matters in that case? So we're going to have 1/12 times the mass times either b squared or c squared. C, exactly. And then about the z-axis, it's the same story, except this time the length that matters is b. So 1/12 mass times b squared. Yes, that's right. Um, and then the third one is a thin disk. Okay, so this one, notice the question is always, so if you have a rectangular plate, are you talking about a rotation like a blade or a paddle? Okay. Like the way it's rotating, if you got your hand in its way, would it slice you or slap you? Okay. That's catchy. I'm going to use that in the future. Mental note. Okay, number 3 is a thin disk. Um, and I'll call that X, that Y, and that Z. About the Z axis, that's like if this disk is rolling. Okay, so any kind of rolling problem or a gear type problem, we're dealing with a rotation about Z. This is 1/2 m r squared. R is the radius of this disk. And the other two, about the x-axis or about the y-axis, if you think about those rotations, it's the same thing because of the axisymmetric, the fact that this disk is axisymmetric. And in that case, you get 1/4 mr squared. So it turns out it's actually a little easier to get a disk rotating like a paddle again than it is to get it rotating like a rolling wheel or like a blade. So notice, think, is it rolling or, paddle? And then the last one is a sphere. And we'll call the radius r again. And because every axis is the same for a sphere, and so all 3 of these, no matter how you orient the axes, are the same. And it's 2/5 mr squared. So with the sphere, it's easy. You don't have to, doesn't matter what the coordinate system, where it's pointed. It doesn't matter which axis you're rotating around. It's always the same. All right, so in which case is it easier to get the object rolling? A sphere or a disk that's like say rolling a penny down an incline or something, if the masses are the same? The sphere is easier than the disk. Does that make sense? Can you make sense out of why that is? So a sphere has, because it bulges out at the So if you're watching it roll from the side, now think of looking at it in the other plane. And that mass is distributed closer to the center because it bulges because of the round sides, you know what I mean? And so the more you have your mass distributed near the center, the smaller the mass moment of inertia is. They, yeah, they would have, so if they had the same mass and the same radius, the same moment applied to both of them would get the sphere moving faster. Yep. And then here's another sort of odd idea. This is all two-dimensional stuff. It might seem a little weird that we have to think about the distinction between a disk and a sphere, but the reason that we have to think about it is because of that fact that um, you know, the mass moment of inertia is determined by how the mass is distributed, how far it's distributed from the axis. And a sphere, even though this isn't happening in the plane that we're looking at, the sphere just does have more mass distributed close to the center. Okay. Any questions? Yes. 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 So just like the center of mass, you know, there's like a way to sum these up to make a complicated shape out of these simple shapes. And in this case, it's even easier. You just add them all up. The one trick is you can't add them up until they are calculated about the same axis. Okay. So if you had, a shape that's like a sphere and a disk and I don't know. Yeah, skinny rod going through all of it. Um, and a rectangle. Um, and if you happen to want to calculate the mass moment of inertia about this axis, then you're in luck. You can just add up those three formulas. But if they're, okay, so if this is A, so for I sub A, just add the formulas. But that's a pretty special case. What about the case where you have a thin rectangular plate and another rectangular plate like that and a, let's say a circle removed here, you know, and you want to calculate this rotation about an axis like this. Well, then you're out of luck as far as just adding the formulas because the formula gives you the mass moment of inertia of this disk about its center of mass. Okay? The rectangle formulas give the mass moment of inertia about the center of mass of this one, somewhere like there, this one, somewhere like there. And all of those, you know, these centers of mass don't agree with the axis that we've chosen overall. So you can't just add the formulas. because the axes are different. They are parallel though. So notice they are parallel. They go through different points. So the fix for that is the parallel axis theorem. So to find the mass moment of inertia about a point other than the center of mass, we'll use the parallel axis theorem. And what this says is, let's say we have this arbitrary object in 2D. And let's say that the center of mass is here. So let's say there's one axis here that we'll call C. And it goes through the center of mass. And then there's another axis that's parallel to C, but it doesn't go through the center of mass. I guess let's call that capital A. That's what I usually use for the axis or the about point in 2 dimensions. And let's say the distance between these two is D. Okay, so that distance D, where along those lines are we talking about that distance? Anywhere, exactly. These two lines are parallel, and that means that there's only one answer for D. If these two lines aren't parallel, the name of the parallel axis theorem gives you a hint that there's nothing you can do. Okay? So for this line C that's through the center of mass, the relationship we have is that the mass moment of inertia of this body about A is equal to the mass moment of inertia. Yeah, no, this is right. Mass moment of inertia about A is equal to the mass moment of inertia about C plus the mass of the object times the distance squared. Pretty awesome. So this M is the mass of the body. This D is the distance between the axes. So looking at this formula, where does the axis have to be for the mass moment of inertia to be small as possible? Center of mass, that's right. So you can't ever get smaller than that because M is positive, D squared is positive. And so any distance you move away from the center of mass for your axis is going to increase the increase the mass moment of inertia. Okay, let's do an example. So let's say we have a rectangle in 2D. Let's say that this is H, this is W, and the mass is M. Let's choose a point A that's at the corner and calculate the mass moment of inertia about A. Okay, well, the formula gives us the mass moment of inertia about the center of mass. So mass moment of inertia about the center of mass is 1/12 times m times h squared plus w squared. And then the parallel axis theorem says the mass moment of inertia about A is equal to the mass moment of inertia about the center of mass plus md squared. What's d squared in this case? So we're talking about this distance d. Half of each of those, right? So yeah, d squared is equal to w over 2 squared plus h over 2 squared. And so that's w squared plus h squared over 4. And so the mass moment of inertia about A is equal to, so I'll write it as 1/12 m h squared. I'm just distributing this 1/12 m through the parentheses in the first formula, plus 1/12 m w squared, plus, so mass times this distance squared gives us 1/4 m h squared plus 1/4 m w squared. And the common denominator for all these is 12. So you can come up with, so 1/12 plus 3/12 is 4/12. And so the answer comes out to this simple formula that, you could use from now on as a formula on its own when your axis is at the corner of a rectangle. And this is equal to 1/3 mass times the quantity h squared plus w squared. And so now, your smartest friend used the integral formula to give you this to represent the mass moment of inertia about the center of mass. And now, you don't have to call your smartest friend. He's probably got a lot of stuff going on. Your slightly dumber friend than that, but still pretty smart. Use the formula that first formula with the parallel axis theorem to give you a new formula that now you can use forever.